Problem: how to design a system will be able to produce a wide range of the fundamental frequencies. Remember, for a string, the fundamental frequency is 1 divided by 2L times this square root. Tension divided by mass per unit length, mu. Piano ranges from 27.5 Hertz to 4186 Hertz. So here 27.5, and the last is the lowest frequency, and the highest is 4886 Hertz. Okay, shear A0 here. A1 here is a double of, it's 27.5, and then it's just an example, 55, and then 210, 220, 440, and 880, 1760, 3520, all multiplus. There's multiplus of 27.5 Hertz. The tension should be fairly constant to avoid deformation of the structure. T should be fairly constant. Okay. If we keep mu constant as the mass per unit length constant, yes, we can say in the formula 27.5 in this formula is 1 divided by 2 times L low times the square root, and the same 4186 is 1 divided by 2 L high times the square root. And if we make some calculations, that means that L low divided by L high is this fraction, 4186 divided by 27.5 is 152.18. It's just simple calculation. If a string for the highest mode is 10 centimeter, then the length of the string for the lowest possible lowest note should be 15 meter. The lowest one is 152 times 10 centimeter is 15.2 meters. So it doesn't work. If we keep L, the length, and the density constant, what happens then? We have mu, the mass per unit length is rho times p times the diameter squared divided by 4. Just normal, it's just simple geometrical terms. Mu is the mass per unit length, rho is the density, mass per volume, and d is the diameter. We have those two equations again. Yeah, and now we have to find out the relation between d low and d high. And then this again is 4186 divided by 22.5. Beware, remark that inside the square root there's a d squared. So we get this again. We get this relation 152.18. That means that L low divided by L high is the same as D low divided by D high, 152.18. 1.8. If the diameter strength for the highest mode is 1 millimeter, then the diameter of the string for the lowest mode is 152 times as big. It should be 15 centimeters, and it's too much. So if both the length and the diameter are varied, in this paraphrasing, we have this term for frequencies, for fundamental frequency, and it can also be written like this. Then we get some other lengths and diameters here. See here, the length goes from 11 to 34. It's 3 times more, but it's not 150 more. Diameter goes from 0032 to only almost a doubled. So please note, strings of similar color and diameter are one continuous length and need to be cut. Okay. There are some nylon strings and so on. But it should be work like that. If you vary both the length and the diameter, so you can make an instrument. To the right we have a harp. We have solution 2. We vary diameter and row. The diameter and the mass density. What happens then? We get here a bandurria. We have the bridge here. It's called the bridge here for the strings. Oh, it's so fantastic. It's beautiful. Problem. The string equations is only true for ideal strings. In reality, 4 aspects should be considered. Fn is n divided by 2L times the square root tension in the square root of tension divided by mass per unit length. N is 1, 2, 3, 4, 5, and so on. L is length, T is the tension, and mu is the mass per unit length. Deviation 1. The string is not totally fixed at both ends. The vibration of a string are transmitted to the body through a bridge. It's a little bit important to understand. Here I have the string, and the vibration is transmitted to the body through a bridge. And the body is called a resonator. As the end correction should be considered to calculate the effective length of an open tube, the movement of the bridge will also affect the effective length of the string. So end corrections for open tubes corresponds to movement of the bridges for the string instruments. Yes. Deviation. It was deviation 1. The string is not totally fixed at both ends. Deviation 2. The string can be inhomogeneous. A change of density can create a partial reflection of the traveling wave and produce some inharmonicity. Here I have before reflection, a wave, smaller mu mass length, what's called mass length per unit length, mass per unit length, and meets a bigger string, a heavier string. And after reflection, the reflected wave is in the opposite direction, and the transmitted wave have the same shape as the incident wave. Okay. And in another situation, we have a string with a bigger mass per unit length meets a thinner one. Incident wave goes in this direction, and this waveform moving upwards. After reflection, yeah, the wave is smaller amplitude, but the transmitted wave have the same shape upwards as the incident wave. So this is a different situation from the first one, as you can see. Deviation number 3, the effect of the fretboard. And fretboard, that means guitar bånd in Danish. Difference of height difference between the saddle and the bridge. Height of frets and additional pressure of the finger to yes, a compensation needs to be introduced, but will depend on the anatomy of the instrument and the dimension of the string instruments. We have here a saddle, okay, and a knot. Frets here, fingerboard, and X0, this distance between the set and the knot. Yeah. So, yeah, fingerboard here, pressure, okay, I try to read it. Geometrical deformation model of a guitar string. In part A, we show the original string in black of length L0. L0 is yeah, and the deformed string in red length L. Okay, when it is pressed between frets E and I and I minus 1. Okay. In part B, we show the details of our deformation models in terms of the 4 different sublengths LE1 to LE1 minus 1 of the deformed string. Sorry. In part B, we show the result of our information model in terms of the 4 different sublengths I1 to LI4 of the deformed string. Yeah, you can see it here, I1, Li2, Li3, or is it yeah, I think it's an I1 and I2 and I3 and I4. And deviation 4, the string has some stiffness, as a string needs to transmit energy to the bridge. Yes, a perfectly flexible string will be very inefficient. And then there was the Young modulus elasticity stiffness. Young modulus is Young's modulus have the same entity as pressure Newton per square meter. For instance, concrete have 26 times 10 in 9 Newton per square meter. Okay. So a measure of the ability of a material to withstand changes in length with under force, equal to the longitudinal stress divided by the strain, and the rubber should not be a good one. I couldn't